This lecture is part of a series of lectures for Rad229, MRI Signals and Sequences, offered in the Department of Radiology at Stanford University. The second lecture, Case-Based and Imaging, is broken down into 4 parts, and Lecture-02A covers magnetic field gradients. The learning objectives for this sublecture include describe 3 different roles for gradients, compare the spatial and temporal characteristics of the gradient fields to both B0 and B1, be able to define the magnetic field at any point in space when a gradient is applied, explain how gradients are used to manipulate either spin frequency or phase, and compare the assumptions between the B0, B1, and gradient fields. This is another diagram of the hardware components inside an MRI scanner, and we can see in green the Z gradient coil, in red the X gradient coil, and in yellow the Y gradient coil, as well as the transceiver, which is used to transmit the B1 field and can also be used as a receiver for the B1 field for signal reception. This is actually a hardware teardown during the installation of a new gradient set, and you can see on the inner aspect here, the circular hardware component here is the magnetic field gradient component. Across the top here are the currents being supplied to this. It's difficult to read. This is the Y, X, and Z gradient coils current supply. So these are very thick copper cables supplying very high voltages and amps to drive the gradient coils themselves. And because so much power is delivered to these coils, there's the need for internal water cooling. And so these lines here actually allow for the exchange of water in and out of this gradient system. And this is typical of high-performance MRI systems in clinical MR systems today. So let's think about the principles of the gradient field and in particular the primary function. The primary function of the gradient is to encode spatial information, and this will occur in a series of 3 steps that we refer to as slice selection, phase encoding, and frequency encoding. And we'll get some insight to these 3 steps of spatial encoding in this sublecture. There are some secondary functions as well. Gradients can also be used for spin dephasing, which may be useful to minimize artifacts, and these are sometimes called crushers or spoilers. They can also be used as spin rephasers after, for example, slice selection, an example of which we'll see later in this lecture, and spin prephasing before the so-called readout gradient. And these concepts may not yet be familiar, but they'll be touched on later in these lecture series. And we can also use gradients to sensitize or desensitize images to motion. And this is really important in the field of things like diffusion-weighted imaging and phase contrast imaging for measuring tissue velocities. Gradient characteristics, this is a nice comparison, or could be used as a comparison to the B1 field characteristics and the B0 field characteristics. And I think of the gradients as being intermediate in strength because they're somewhere between the B1 field and the B0 field. So a typical gradient system, high performance system, would be rated at 80 to 100 millitesla per meter, or 8 to 10 Gauss per centimeter. And if you just simply think of the units here as being units of field per distance, then we can multiply these kinds of applied field strengths by the nominal dimensions of a field of view that we might be interested in. And we can see that we would arrive at about 150 Gauss, or 0.015 Tesla. So these fields are gradient fields, the maximum fields generated rather, are on the order of millitesla. And these millitesla gradient fields can add or subtract to the underlying B0 field. And importantly, they're parallel to the B0 field. That is, they only add or subtract to the B0 field along the Z direction. So you may already have some familiarity with X gradients and Y gradients and Z gradients, but the magnetic field component of each of those gradients is pointing strictly along the Z direction. As the name implies, they are spatially varying. These are linear B-field gradients. We treat them mathematically as being linear, and we'll talk about some non-idealities in later lectures. And they're temporally dynamic on a scale of kilohertz. And so we can slew these gradients, that is, we can turn them on very quickly. We refer to that as the slew rate, and maximum typical slew rates are about 200 Tesla per meter per second. And that means a very high performance gradient system might have a rise time of about 500 microseconds. That is the time it takes to reach the maximum gradient strength when using the maximum slew rate. Importantly, gradients are not fields perpendicular to B0. So while the GX gradient may sound as if it could be generating a field perpendicular to B0, which points along the Z or K hat direction, remember these fields strictly point along the K direction, but are gradients along the X, Y, or Z direction. And this will become more clear when we develop the mathematics and show some diagrams as well. So let's think about the Z gradient coil because it's designed differently than the X and Y gradient coils. It's typically what we call a Maxwell pair coil. It generates a linear B field variation along the Z direction, and it's highly uniform in the XY plane, what we sometimes call the transverse plane. And to generate such a field, we have windings of coil inside the magnet, inside the gradient set, and we can apply currents that are equal and opposite in these two windings of coil, and consequently increase the field at one end of the scanner slightly and decrease the field at the other end of the scanner slightly. And we thus have a linear variation in the magnetic field along the Z direction when using the Z gradient. And in comparison, we can see an example here of the X and Y gradients. These are typically designed using so-called saddle coils or Golay coil pairs. And they generate a linear B field variation along the X or Y directions, but again, fields that point strictly along the Z direction, or at least in the ideal case. These are also highly uniform in the YZ or XZ plane, respectively. And it's really the innermost turns that produce the magnetic field gradient. So you can see there's a relatively extended hardware element here, but it's the end current or the end wiring element here that really generates the important component of the magnetic field. And in this case, this is a magnetic field gradient that's generating a gradient, say, in the X direction here. And so this Golay coil pair, when charged with current, will generate a larger amount of magnetic fields, say, at the positive X direction, and a slightly opposing amount of field in the minus X direction, and will consequently give us a gradient in the B0 field, or the background field, as a function of the X direction. So let's look at an example here. So this is an example of spins in the MRI scanner. And so we can see here, perhaps this represents a slice location in a subject that would correspond to the spins that are along this dimension here. And as we look at what's happening to the spins to the left and right of this particular position, we notice a couple things. Firstly, at this centerline position here in particular, the spins are not moving. And that's because the coordinate system that we're in is the rotating frame for this example. And when we charge, that is activate the X gradient, which is left-right here, we can cause a slightly higher field to be exerted, say, on the far right-hand side here, and the spins will precess more quickly than the rotating frame. Or we can cause a slight decrease in the magnetic field, and the spins will actually slow down some. And if the magnetic field is causing the spins to slow down, then they actually appear to be slightly rotating in the opposite direction. So this is an example of spin precession, but in the rotating frame in the presence of an active X gradient. We can do the same thing for a Y gradient. And so here we've activated the Y gradient, and we can see again that the spins have a distribution of frequency, even in the rotating frame, from, say, the top of the scanner towards the bottom of the scanner. And interestingly, and one of the really important features of gradients is, of course, we can activate both of them at the same time. So in this case, if we've activated the X and Y gradients at the same time, then we'll have a plane of spins here, what we call an isochromat of spins, because they're all precessing at the same frequency. This will be exactly at 45 degrees if we've activated both coils equally. And as we move along the gradient direction, that is sort of along this sort of 45 degrees, then we'll come to a location here where the spins are moving quite a bit more quickly, and we can move in the opposite direction and see that spins are precessing with the opposite handedness in the rotating frame. So by changing the amount of current driving each of these different coils, we can actually move this plane around. We could rotate this plane around, for example, to be purely in the X, purely in Y, or somewhere in between. Okay, so that was some nice overview qualitatively of what magnetic field gradients do. Let's look more carefully at the mathematics of gradient fields. So gradients are a special kind of inhomogeneous B field whose Z component varies linearly along a specific direction called the gradient direction. And this is a little bit cumbersome to look at, but let's break it down. So on the left-hand side here, what we're denoting is a B field from a gradient, just B sub G. And we specifically note that this is B sub G that points along the Z direction, because this is the only magnetic field generated by a gradient field. And here's where we define which direction is actually varying. So this is a variation in the B field along the X direction. And by definition, we relate this to the applied gradient field. So this is Gx, the X gradient amplitude, and a position. So this position is relative to isocenter, something we'll talk about shortly. And so what this says is that depending on the gradient of the amplitude, the magnetic field gradient, the B field that you will generate depends on the position. So if the position is 0, then the gradients will generate no additional B field, and so you would just have the B0 field locally. But as you get further and further away from isocenter, then the action of this gradient field will generate a larger and larger field, and hence a spatial gradient in the B field. Okay, so let's look at this as how we actually use gradient fields. So this is an X gradient again, and this is what we call a pulse sequence timing diagram. And it's just an example of when we turn a gradient on. So we're turning the GX gradient on. It stays on with constant amplitude for some period of time, and then we turn the gradient off. And what that means as a function of space is that at any point in time when this gradient is turned on, we have a magnetic field gradient across the X direction. And so the B field that points in the Z direction but becomes a function of X. We can make the magnetic field gradient lower, so we can change its amplitude to be lower by turning down the amount of current driving the gradient coil. And consequently, we will have a lower gradient of magnetic field, say along the X direction here. We can, of course, define the same magnetic field effects for the Y gradient and the Z gradient. And when it comes to working with, say, the equation of motion, what we care about is the B field being generated by the magnetic field gradient. But it obviously depends spatially on either the X, Y, or Z positions or any combination of the three. And so we need to know the gradient strength, and we need to know the position of the spin of interest. So let's look at combining these things, because those magnetic field gradients can be activated independently and simultaneously. And so here we're simply adding up the different magnetic field gradient components, and we can write this finally in vector notation to say that some gradient vector, which has X and Y and Z components, is a function of time. When we dot it with a position inside relative to isocenter, that will tell us the magnetic field that's being generated at a particular point at a particular time. And gradients contribute to the net B field, but again, only along the Z direction. And so here, if we want to describe what's the total magnetic field at a point in time, then of course we would still have the active B0 field plus the B field from the gradients. And we notice that these point along the k-hat prime direction. And we can expand this out to be a slightly more general form, or slightly more widely used form, which just shows that the total magnetic field in the presence of both B0 and a gradient depends on the gradient as a function of time and the position itself. So how far away are we from isocenter, and what's the magnitude of the gradient being applied at a particular point in time? So let's make a comparison, now that we've seen some mathematics of the gradient fields, between the various assumptions that we use in MRI. So if we return to thinking about the B0 field, we remember that it's perfectly uniform over space. We refer to this as B0 homogeneity, and perfectly stable with time. And so the expression that we used is this simple one on the right, where we see that the B field is in no way a function of space or time for the ideal B0 field. The B1 field, however, is also perfectly uniform over space. We refer to this as B1 homogeneity, but it's obviously temporally modulated exactly as specified. That is to say, we have a precise B1 envelope function and a precise carrier frequency that gives us some B1 dynamics, if you will, that allow us to control the spin system through the process of forced precession. And then the gradient fields, we assume that they're perfectly linear over space rather than being uniform over generating uniform fields as B1 and B0 did. And we refer to this as gradient linearity. And they're also temporally modulated exactly as specified. So they vary over space and they vary over time. And we can see that explicitly in the mathematical expression describing the B field generated by the applied gradient fields. So let's return to thinking about the Larmor equation and what happens when we activate magnetic field gradients. So we remember that the Larmor equation arises from free precession in the equation of motion. And in this case here, we would need to substitute what is the applied magnetic field with the applied gradient field. Gradients contribute an additional B field that is both space and, in this case, also time dependent. Here we're thinking about things only in the rotating frame. And so this is the additional magnetic field that we need to consider when trying to evaluate what happens to the frequencies of the spins. And so now we see that the Larmor frequency becomes a function of both space and time because the gradients were a function of time and the magnetic field generated depends on the position of where you are in time. And so we can now understand that applied gradient fields spatially change the local Larmor frequency. So let's look again at how we might generate frequency as a function of space. This is a simple pulse sequence diagram where we turn a gradient on for some period of time and then we turn the gradient off. If we look at the magnetic field that would be generated by such a gradient, we can see that at isocenter, because that position is 0, we would generate no additional magnetic field. But as we move further and further away from isocenter, we would generate larger and larger magnetic fields, and we would do so in a linear fashion for an ideal gradient. And what this means, according to the slide, the equation we had on the previous slide, is that as we move further and further from isocenter, we will have higher and higher precessional frequencies. So close to isocenter, and perhaps this is the frequency of precession inside a voxel. That's what the white box is meant to indicate. When we're close to isocenter, then the frequency of precession is relatively low, if you will. And as we move further and further and further away from isocenter, then the frequency of precession is becoming higher and higher, again, in the presence of a magnetic field gradient. So what happens when this gradient is turned off after some period of time? And this is actually a really interesting aspect of MR. And so let's remember that the phase that we would generate from a gradient arises as the integral of the applied frequency. And in this case, the applied frequency is the gradient magnetic field dotted with some spatial position. So this gives us the fundamental frequency of precession, if you will. And if we integrate or follow that frequency for a certain period of time, then we'll arrive at a phase angle. If it's just a 1D rectangular gradient waveform, that is, we turn a gradient on, we turn a gradient off, then this expression simplifies to just being the gradient amplitude that's applied, how far away you are from isocenter, and then the time interval that you specifically care about. And so in this case of a gradient being turned on for a finite period of time and then being turned off, we could identify that the amount of phase we would accrue from a gradient would be longer, or longer times would confer more phase, and stronger gradients would also impart phase more quickly. And so depending on the specific needs of a pulse sequence, we could design this magnetic field gradient to either be stronger or weaker. So let's look at what happens to the spin system again. So here's a pulse sequence diagram. We have a magnetic field gradient that we're turning on for some period of time and then turning off. As we saw previously, at any point in time when this magnetic field gradient is turned on, we have a spatial variation in the magnetic field. So magnetic fields are higher as we get more and more distant from isocenter. And as we saw previously, as we move from, say, one voxel to another voxel to yet another voxel that are further and further away from isocenter, inside those voxels there will be different precessional frequencies going from low, where the magnetic field generated by the gradients is low, to being relatively high frequencies where the magnetic field generated by the gradient is higher. And if we turn this gradient off at some point in time, and perhaps we do that at an earlier point in time, then the spins will inherit some phase, and that phase will simply depend on how long was the magnetic field gradient turned on for. And so at the end of the application of the magnetic field gradient, the spins are pointing in a particular direction, and we refer to that as the phase. Now, if we extended the duration of the magnetic field gradient, so we played that same gradient for a longer period of time, we would still be playing the same magnetic field gradient, so this would still spatially look the same, but because we played it for longer, the phase of the spins will be different. And so they'll carry on at that same frequency, but for a slightly longer amount of time, and they'll cruise slightly more phase. And as one more example here, you can see the magnetic field gradient is turned on just a little bit longer. And each of these spins at this point, or bulk magnetizations rather, has accrued the same amount of phase at this particular point in time. And so we can see that by extending the interval of the magnetic field gradient, we can change the amount of phase at each spatial position, depending on the duration of the magnetic field gradient. So how are gradients used for spatial localization? For that topic, you'll have to follow the next lecture. Thanks for joining us again for Rad229 MRI Signals and Sequences.